and that's kind of what it is in reality.
Okay, thank you.
Okay, it's 5:30, so let's go ahead and get started today. All right, good afternoon, everybody. How's everyone doing today?
Hello.
Hey.
Wait, can you guys hear me?
Yep, I can hear you.
Are we picking up from upwinding?
So we finished upwinding, but we're going to I'm going to show you the MATLAB portion of that example, because I think we skipped that last time, and then we're going to jump into 2D convection diffusion today. Before we do that, I have a couple announcements though, mostly just regarding the exam. So I graded your guys' exams on Friday. So you know, some of you guys have already noticed the grade. So you know, if you want to look at the feedback or the comments that I left, I think you can click on the assignment and then you can read my comments from there. So you know, if I only left comments if I you know thought the answer was not correct. So, but if you had the answer correct, I didn't leave any comments on that. So so you guys did really well. So the average on the midterm, oops, I go to pen mode. It was like what, Mario, 43.8 out of 50, something like that. Right? So that's approximately like 87.5%. So you guys did really well. So that was you know, that was a really good average. So you know, those grades should be in. So double check. So I've already had someone come and tell me that I didn't see the last page of his work, so I missed grading that. So please make sure that I graded everything correctly. I looked at the you know, I checked all your answers well, and you know, everything's input, everything adds up correctly. So you know, definitely make sure I did that. Right. So besides that, I'm working on the final homework assignment. So there's one more homework assignment, because I want you guys to get some practice with higher order schemes, which is going to be the lecture after this one. So just so you know, you can practice it a little bit before getting into the project. And then, you know, since there's only one more homework, because I want you guys to focus on your final project after that. Let's see what else. I think that's it. Are there any questions for me about the exam or just anything in the class before we get started today? Okay, let's go ahead and get started. So let's pick up where we left off last time. Okay. So let me just write out. Let me write out what the equation for that example was, and then I'll share my laptop screen and test the code. Okay. So we're working on this example. So which was a 1D convection problem with finite volumes. Right. So the problem was 5 du or d phi dx minus 8 d squared phi dx squared is equal to 3x. Okay. And then our boundary conditions, we had 2 of them. So the first boundary condition was phi at 0 is equal to 10. So this was a Dirichlet boundary condition. And then our other boundary condition was the flux at x is equal to 1 is equal to 3. Okay. So remember, now that we're doing convection and diffusion for finite volumes, we kind of changed the definition for the Neumann boundary condition. So before, our Neumann boundary conditions was always the derivative, but now what we're going to be doing is we're going to say is the total flux at those cases. Okay. Mostly just for mathematical convenience. Okay. So there's a question in the chat. So the question is, what is today's topic? So today's topic, we're going to continue kind of where we left off for finite volume convection problems. So what I'm doing is I'm kind of finishing up the example that we kind of left hanging at the end of last time, mostly just to cover the MATLAB portion. And then from there, we're going to start to go over 2D problems with convection and diffusion with finite volumes. Okay. So last time, so this is the example that we went over. So let me write out the parameter values before we jump into MATLAB. So from this equation, you can see that we have a 5 in front of the convection derivative. So this tells us that our u parameter is going to be equal to 5. we have an 8 in front of our diffusion term. So our diffusion coefficient K is going to be 8. Okay. And then our source is going to be 3x. Okay. So keep that in mind as we look into the MATLAB code. Okay. So let me share my, my other screen. Okay. So here's the MATLAB code that I posted on Titanium. So this should be the 1D convection problem with finite volume. So you should see it at the top of this week's Titanium page. Okay. So this code is structured basically the same as we always do. So section 1 is we're going to list out all our parameter values. So the one that I want to draw your attention to is these two lines. Okay. So just like before, we have, or just like we just said, we have K is equal to 8, so that's our diffusion coefficient. And then next we have U is equal to 5, which is our convection velocity. Okay. So I have it in terms of this just so that later on when we're plugging into the equations, we can basically put it in the exact same form that we had before. Okay. So just like always, the meat of this problem is going to be within section 2. Where in section 2 we have our loop, where this for loop has the same function as it always is. So in this for loop, we're going to visit every single cell. Okay. And then depending on where the cell is located, we're going to do something different. Okay. So first, let's actually look at the else case. So this is as indicated by the comment here, this is the case when we're at an interior cell. So when we're at an interior cell, we have both neighbors on the left and the right. Okay. So you can see here we have A at I cell, comma I cell plus 1. So this is the coefficient for the right neighbor. Next, we have A at I cell, comma I cell minus 1. So this is the coefficient for the left neighbor. And then this value right here, A at I cell, comma I cell, this is the coefficient for the central cell, or for myself. Okay. Okay. And you can see that these coefficient values, they're consistent with the equations that we went over last time in the lecture. Okay. And then we can't forget the source term. So our source term, remember, was 3 times x, and then due to the finite volume method, we multiply that by dx, or the grid spacing. Okay. Okay, so then now let's go into the other parts of the for loop, so or the if statements. So the first thing we have if I cell is equal to 1. So just like this comment says right here, so if I cell is equal to 1, that tells us we're on the left side of the domain. So we're on the leftmost cell. So on the leftmost cell, we have our Dirichlet boundary condition. So you can see that Dirichlet boundary condition is incorporated into the right side of the equations from this term right here. Okay. And then for the left-hand side matrix A, we only have entries for the central cell and then for the right neighbor. Because remember, when we're on the total left side of the domain, we don't have a left neighbor, so there's no way for us to incorporate a coefficient there. Okay. And then for the if we're on the total right side, so if I cell is equal to n, then we have our Neumann boundary condition, or the flux boundary condition that we talked about before. Okay. So in this case, we only have a neighbor on the left. So we have A at I cell, comma I cell, and then A at I cell, comma I cell minus 1. Okay. And then these are the coefficients that we talked about last time. And again, we have the right-hand side of the equation, which is our source term, and then our Neumann boundary condition right here. Okay. And then from here, we can solve it. And then in this case, since it's a 1D problem, I've included the exact solution here. So let's go ahead and run it. Okay. And you can see that in this case, which I made it a pretty hefty simulation. So I made it 500 cells. So in that case, the solution is pretty much on top of each other. So you can't see the blue curve, but there's a blue curve that's underneath this red one, which shows that those two equations, or the two methods, show the same solution. Okay. All right, any questions on this? Okay. So there's no questions. Let me bring back my iPad. And then we'll get started on 2D equations. Okay. Okay. Okay, so then now we're going to start 2D convection diffusion. With finite volumes, okay, with FVM. All right. Okay, so our starting point here is going to be our conservation equation. So it's the same as we started in 1D, but in this case we're going to do the integrals in 2 dimensions. Okay, so our starting point is this right here. So we have a nabla dot product with our velocity vector times phi minus k nabla dot product with gradient of phi is equal to q, where since we're in 2D now, our q is going to be a function of x and y. And then just like we always do in the finite volume method, we're going to integrate this over the cell. Okay. So then that gives us, since our cell is a two-dimensional object now, we're going to have a double integral. Okay. So we have double integral over the area of nabla dot product with v phi dA minus k integral of on A of nabla dot with the gradient dA. Okay, and this is all equal to integral of q of xy dA. Okay, and so just like we did with the diffusion case, we're going to take all these integrals here, where you know they're integrals of the convection term and the diffusion term. Okay, and what we're going to do is we're going to convert them to line integrals using the divergence theorem. Okay. So I do want to clear up kind of one point of confusion that I saw on the midterm. So this is regarding the conceptual question on the how many integrals do you get by applying diffusion theorem on or divergence theorem on a cube. Okay? So you can only apply divergence theorem if your integral has this this nabla product right here. Okay, so in particular, it's that nabla dot right there. Okay, so because what I saw a lot of people do on the midterm was they took the triple integral on the cube and they converted to surface integrals using the divergence theorem. And then what they did was they converted those surface integrals to line integrals. But you can't do that because once you apply divergence theorem once, then you can't really do it again unless you have this guy there. Because usually after you apply divergence theorem once, then that guy kind of goes away, which is kind of what we want. Okay. All right. Any questions on this before I turn the page? Okay. Okay. So applying a divergence theorem on those, we get a line integral. So I'm just gonna, because the diffusion term and the convection term, they both have the same expression, I'm gonna club them together into the same integral. So then what we get is the line integral around the boundary of our cell of phi of v dot product with n minus k gradient of phi dot product with n, right? ds is equal to integral of q x y dA. Okay. where now this guy, these integrals right here, this is going to be kind of the bulk of our focus here. These represent the combined convection and diffusion flux across the boundary. We're just like before, this first integral term right here with the v, because this v is our convection velocity, this is convection. Okay. And then since this other part of the integral has a k, this part right here represents diffusion. Okay. Okay, so then let's draw our typical cell. So our typical cell looks like this. So then let's label the faces according to their compass directions. So first we have an N for the north face, E for the east face, S for the south face, and W for the west face. Okay. And then since we need the normal vectors, let's go ahead and put those in. Okay. So the normal vector on the east face is going to be 1, 0. And then on the north face, our normal vector is going to be 0, 1. On the south face, the normal vector is going to be 0, -1. And then on the west face is going to be -1, 0. Okay. And so in order to evaluate those line integrals that we have above, what we need to do is we need to dot product a vector with these normal vectors. Okay. Okay. So we have two integrals that we need to evaluate. So for the convection integral, we take the dot product between the velocity vector v and hat. Okay. So remember, just as a reminder, our velocity vector looks like this. Okay. So it has two components. The x component of the velocity vector is given by u, and then the y component is given by v. Okay. And then the other dot product that we have to perform, which is review from when we did diffusion with finite volumes. The gradient of our solution phi is given by d phi dx, comma, d phi dy. Okay. So when we take the dot product between these guys and evaluate it on each of those different faces or each of the different sides, we're going to get 4 different integrals that involve the velocity components, the partial derivatives, and either a positive or a negative, depending on which side of the square that we're on. Okay. All right. Any questions on this before I turn the page? Okay, so let's write out the expression for each of the different integrals. Okay, so just like we did in diffusion, we're gonna have 4 different integrals, one for each side of the square, right? So let's start from the east and then work our way clockwise around the square. Okay, so let's start with the east integral. Okay. So on the east, we have integral on the east of phi v dot n minus k of gradient of phi dot m ds. Okay. where remember on the east face, our normal vector is a 1, 0. Okay. And so one other thing that I'm going to do is after we take the dot products, I'm going to apply trapezoidal rule so that we can kind of simplify these integrals and turn it into an algebraic expression. Okay. And so once you do that, you're left with the following expression. Okay. So first, let's do the convection term right here. Okay. So v dot n, where v vector was the vector u comma v. So when we dot product that with n, which is 1, 0, all we're left with is u. Okay. Or in other words, just the x component of velocity. Okay. And then we apply the trapezoidal rule on the phi value, and then we get phi at little e, which is the solution value at the east face. Okay. And then from that, we're going to subtract k times gradient of phi with a vector dot n. Okay. And so that that's going to be k d phi dx on the east face. Okay. Because remember, since the gradient of phi is a vector, once we take the dot product with n, then we're only left with just one component. So the one component in this case is the x component. So we have d phi dx. Okay. And then when we apply trapezoidal rule, we also have to account for this guy. Okay. So the east face, we have to multiply by the length of the east face. So the length of that face is going to be delta y. So that's our integral on the east face when we combine both convection and diffusion. Okay, I'm boxing this one just because it's going to be important to know once we start applying boundary conditions, because once we apply boundary conditions, it's usually best to kind of work off these integral terms right here. Okay, so that's the east integral. So that's 1 out of 4. So let's keep going. So if we work clockwise from the east face, then the next one we're going to go is south. Okay. So for the south face, we have the same expression, except on the south face. So we have phi v dot n minus k minus k times gradient of phi dot n hat ds. So in this case, we're going to end up with a different expression because our n hat is different. Okay. So this integral actually right here is the same as this one right here, but it's just how you apply it with the n hat that's going to make it different. Okay. So for the south face, our normal vector is a 0, -1. Okay. So that's going to be, it's going to make things almost completely opposite from the last case, because we're going to multiply things by -1 because we have this minus here. And then instead of the x component of our vectors, we're going to take the y component because our n hat is 0, -1. Okay. So then if we do that and we apply our trapezoidal rule as before, we end up with this expression. So we have minus phi little s times v plus k d phi dy s times delta x. Okay. So you can see it looks similar to our expression for the east face, except instead of the evaluating things at little e, we evaluate things at little s because that's the south face, and then we flip the signs and everything. Okay. And the reason for that, again, remember, is the normal vector on that south face has a minus out in front, so that means we have to flip the sign. And then for all the vector, and then for the vector terms, for the convection velocity and for the gradient, we take the y components of those instead of the x, because that's what happens when we dot product with the n hat. Okay. All right, so I think I can squeeze one more onto this page. Okay. So then let's do the integral on the west face. Okay, so we start with the same integral. So we have the integral on the west face of phi times v dot n minus k times gradient of phi dot n hat ds. Okay. So for the west face, we have a different n hat. So our n hat's going to be negative 1 comma 0. Okay. So then if we do that, if we use that and we apply trapezoidal rule, we end up with the following expression. So we get a minus phi w times u plus k minus phi w times u time plus k d phi dx at the west face times delta y. Okay. So it looks similar to our east face because they're both, the vertical faces here, except the signs are reversed. And then instead of evaluating things at little e, we apply them at little w. Okay. All right. Any questions on this page before I turn it? Okay. Okay. So that's 3 out of the 4. So let's do the last one. Okay. All right, so now the last one is the north face. So we have integral of n of phi v dot n minus k gradient of phi dot n ds. Okay. And then for the north face, our n hat is going to be equal to 0 comma positive 1. Okay. So then if we perform those dot products and apply trapezoidal rule, we end up with the following. Okay. So we have phi n times v minus k d phi dy at the north face, okay, delta x. Okay. So again, we so because our n hat is a y component, so it's 0 comma 1, we take the y components of all of our vectors. So that's where the v and the d phi dy come from. And then since it's a positive 1, we keep the same signs from the integral. Okay. Okay. So those are the direct kind of the direct application of trapezoidal rule on the 4 integrals. Okay. But we still have a problem right now because right now everything is in terms of the face values or the values on the sides. Okay. Because remember, when we do finite volumes, we always put things in terms of the self-centered values. Okay. So we need to put this, we need to put these we need to put these equations in terms of the self-centered values. And so to do that, we're going to apply, the same kind of linear profile that we did before. Okay. So let me draw out the cell and all of its neighbors. Okay. Okay. So we have our little D-pad here for the cell. Okay. All right, so just like before, I'm going to use phi sub c to denote the center cell. So that's the cell of interest. Okay. Right. And then just like before, I'm going to use capital letters to denote the neighbors, the values of the solution at all the neighbor cells. Okay. So we have phi sub capital N for the north neighbor, phi sub capital E for the east neighbor, phi sub capital S for the south, and then phi sub capital W for the west neighbor. Okay. And so what we need to do is we need to make 8 approximations because we need to approximate both this guy, which is just the value of the solution at the cell face. Okay. And then we also need to approximate this guy from our diffusion term, which is the derivative of the solution at the cell face. Okay. So what I've indicated in X's right here, these are the kind of the cell side values where everything is in terms of right now. Okay. So need to approximate values at the X's with the cell-centered values. Okay. So let me do a couple of them on this page, and then I think the rest will spill over. So let's start with the east face because we started our integrals there. Okay. So if we want to approximate phi comma little e, okay, that's the kind of the location which I've circled right there. Okay. We're going to use the same approximation that we used in the one-dimensional case, where we say that phi sub little e is going to simply just be the average of the two cells that it neighbors. Okay. So this space right here, where the x is, it's the two cells that it touches are phi sub big C and phi sub big E. Okay. So what we can do is we can approximate phi sub little e with kind of the average of those two. Okay? So we can say that this is going to be equal to phi sub big C plus phi sub big E, all divided by 2. Okay. Okay. And then the other thing that we need to approximate is the derivative. So this is the same as we did for diffusion. So I'm not going to go over it too much again, but remember this results from the fact that we assume there's a linear variation between phi sub E and phi sub big E. Okay. Let me move it up a little bit. Okay. So just like we did with diffusion, this is going to be the cell-centered value on the right of the face, which is phi sub big E minus phi sub C, all divided by delta x. Okay. And so what we're going to do is we're going to take these approximations and then plug them into our integrals so that we get everything in terms of the self-centered values. Okay. Are there any questions on this? Okay. Okay. So just for the sake of completeness, I'm going to write out kind of the same expressions for all the other things that we need to approximate. Okay. So now let's do the ones at the south face. Okay. So we have phi sub little s. So this comes from the convection term. So that's going to be phi sub big S plus phi sub C, all divided by 2. Okay. And then d phi dy at the south face is going to be phi sub c minus phi sub s, all divided by delta y. Okay. All right, so then now we have the west face. Right, so that's phi sub little w. All right, so phi sub little w is going to be phi sub big W plus phi sub c, all divided by 2. Okay. And then the derivative at the west face, d phi dx, is going to be phi sub c minus phi sub w, all divided by delta x. Okay. And then finally, we have the north terms. So we have phi sub little n is equal to phi sub big N plus phi sub c all divided by 2. And then we have d phi dy at the north face. Okay. This is equal to phi sub big N minus phi sub c, all divided by delta y. Okay. And so remember, to be careful with the derivative terms here. Okay. Because the ordering here is important. Okay. So make sure you put the the terms in the correct order. Okay. And so now that we have these guys, we can plug them into all the integrals. Okay. So then we'll get new expressions for the integrals that are in terms of the self-centered values, which is what we want, because that's ultimately what we need to solve for using the finite volume method. Okay. Okay. So let me go ahead and plug these in. So let's do the east integral first. So if we plug in the expressions from the previous page, what we get is phi sub c plus phi sub big E, all divided by 2, times u delta y minus phi sub big E minus phi sub c, all divided by delta x times k delta y. Okay. Let me make this a little bit neater. Okay. Okay, so that's the east integral after we plugged in these expressions here. Okay, so now let's do the south one. So for the south, we have minus phi sub c plus phi sub s all divided by 2 times v delta x, okay, minus phi sub c minus phi sub s all divided by delta y times k delta x. Okay. So that's the south integral. Okay. And then we'll do the west and the north integral on the next page. Okay. Any questions on this? Okay. Okay, so that's the south integral. So now let's do the west one. Okay. So on the west integral, we have this. We have minus phi sub w plus phi sub c, all divided by 2 times u delta y, okay, plus phi sub c minus phi sub w all over delta x times k delta y, okay. And then finally, the integral on the north, we have phi sub n plus phi sub c all divided by 2 times v delta x plus, or minus, sorry, okay, minus our diffusion term, which is phi sub big N minus phi sub c, all divided by delta y times k delta x. Okay. Okay. So then now that we have the integrals in this form, we can just simply add them together, and then we'll finally get our expression. So a lot of derivations today, I know, but this is the one that you can kind of plug in for all the interior nodes, okay? Or interior cells, sorry. And just as a disclaimer, I've assumed that our grid spacing is uniform. Okay, so we assume that delta x is equal to delta y, which is equal to delta. Okay, so that helps us simplify things pretty considerably. Okay, so then we end up with the following expression. Okay, so we get u delta all divided by 2 minus k phi sub big E. Okay, so that's the coefficient in front of the east neighbor, okay, plus minus v delta all over 2 minus k phi sub s, so that's the south neighbor, plus minus u delta all over 2 minus k times phi w plus v delta divided by 2 minus k phi north, so that's our north neighbor, okay, plus 4k phi sub c, okay. So that's our that's the coefficient in front of ourself, and then we can't forget our source term. Okay. So then our source term on the right, after we apply our trapezoidal rule, is q of xc comma yc times delta squared. Okay. So this equation that I boxed right here is that this is the equation that you can apply for an interior cell for convection and diffusion. Okay. Interior. Okay. Okay, so then what we're going to do next is we're going to find out, or we're going to see how we apply boundary conditions on this guy. And then after that, we'll jump into an example. Okay. But before we do that, are there any questions on this? Okay. You guys okay today? Hardly heard from you guys today. I heard from someone in office hours this morning that it's there's a lot going on this week with other classes. So maybe probably everyone's just a bit tired, huh?
Yeah, it was a tough week last week.
Oh, I see. I see. Okay. So let's do the boundary conditions now. Okay. So the boundary conditions are going to be a bit more complicated. So if you remember kind of when we were reviewing for the midterm, you know, we talked about how when you're applying boundary conditions for finite volume problems, usually it's a good idea to go and just work off the integrals. So now that we're doing convection and diffusion, that's going to help us out immensely, because it doesn't, I don't want to say it simplifies the calculations, but it helps prevent you from getting too confused. Because when we apply the boundary conditions, what they're going to do is they're only going to affect one integral in our expression. So when you're applying boundary conditions for finite volume problems with convection and diffusion, you only have to modify that integral that it affects, and then all the other ones you can leave unchanged. Okay? So unfortunately, what this means is that when you're working out these problems by hand, the hand calculations get a bit lengthy, just because you kind of have to replace an integral and then work it in together with everyone else. But this is kind of the method that I find that kind of prevents me from getting too confused with kind of the science of things and, you know, where things go. Okay, so let's do our two types of boundary conditions. So first we have Dirichlet. Okay. Which for finite volumes, it's the bit more complicated one of the bunch. Okay. So let's just, as an example, let's say that we have a Dirichlet on the north face. Okay. So we have something that looks like this. Okay. So we have phi sub W, which is the phi value on the west face, phi sub C, which is our central value, phi sub E, our east neighbor, and phi sub S, our south neighbor. Okay. And then on the north, we don't have a neighbor, but instead of a neighbor, what we have is a known Dirichlet value. Okay. And so since we have neighbors on the west, the east, and the south, all those integrals are actually going to be unaffected. Okay. So the only integral that we need to change, or the only integral that we need to update, is the north integral. Okay. And so let's go from the expression that I boxed earlier. So after we apply trapezoidal rule on the north integral, what we get is this. Okay. Okay. So then after we apply trapezoidal rule on the north integral, we get phi sub little n, which is the value of phi on this face right here, where I put the x, minus k times d phi dy at the north face times delta x. Okay. And so let's modify this to account for the Dirichlet condition. Okay. Okay. And so first, let's do this first term right here. So that's phi sub little n, or the value of phi at the x. Okay. So luckily for us, we know exactly what that is, because since we know the Dirichlet condition, we can just directly plug in phi sub 0 for that. Okay. Okay. Okay, so this was our known value. So we have that phi sub n becomes a phi naught. Okay. And then we're going to multiply that by v. Okay. And then from there, we have to approximate our derivative at the face. Okay. There's going to be phi naught minus phi sub c, all divided by delta y divided by 2. Okay. Okay. And all that's going to be multiplied by delta x. Okay. And so what I did for the derivative was the same as we did for diffusion. So we basically take the half distance. So we take delta y divided by 2, and then we take the difference in between the Dirichlet value and our central value. Okay. And so we can simplify this. So let's assume delta x is equal to delta y is equal to delta. Okay. And then if we do that, we can get something that we can plug in directly for that integral. All right, so before I flip the page, are there any questions on this? Okay. Okay, so then if we do that, then we get this expression for the north integral. Okay, so our north integral becomes, so we have integral of phi v dot n minus k d phi dy ds. Okay. So then if we plug in, if we kind of simplify our expression from the last page, what we get is 2k phi sub c, okay, plus phi naught times v delta minus 2k phi naught. Okay. Okay. Where again, just like we saw with diffusion, everything with the phi naught, all that is known. So it's nothing that we need to solve for. So whenever something is known, we can go ahead and move that to the right-hand side of the equation after we add this together with all the other integrals. Okay. So what I've shown you here is just the process to replace the north integral. But to actually solve a problem with this, you still need to evaluate the east, the south, and the west integrals. But those kind of remain unchanged. So that follows kind of the same process that we followed kind of before we got into boundary conditions. Okay. Okay, so then now let's do Neumann conditions. Or as they're better known as flux conditions. That's kind of what we're calling them now. Okay. And so just like we did in the one-dimensional case, the flux conditions will be relatively easy, because what we can do is we can just use these to replace an entire integral. Okay. So then let's take an example where we have a Neumann condition on the east face. Okay. So so for this one, we have phi sub c, and we have neighbors on the west, the south, and the north. Okay. And then on the east face, what we have is a flux, and that's going to be equal to gamma. Okay. And so just like we saw with the Dirichlet condition, since we have neighbors on the south, on the west, and the north, all those integrals become unchanged. So the only integral that we're going to modify is the east integral. Okay. And so let's write that out here. Okay, so we have the integral on the east. Okay. So on the east, we have phi times v dot n minus k gradient of phi dot n times ds. Okay. And then what we're going to do, or what we're saying here, is that this entire expression, remember what we said before, this is the that term that I've kind of put in brackets right there. That's the combined diffusion and convection flux across that face. So what we can do is we can replace that kind of directly with gamma. Okay? And so if we do that, all that becomes just gamma times delta y. Okay? And so mathematically, this becomes a bit simpler than Dirichlet because we don't have to kind of approximate that derivative in kind of a weird way. We just kind of plug in directly for that flux, and then it becomes something pretty simple. Okay. Okay. Any questions on this? Okay. So let's take a look at an example. So probably what we'll do is we'll start the example today. Hopefully we'll get through a lot of the hand calculations, and then next time we'll finish up with the MATLAB code. Okay. Okay. So in this example, we have the following problem. So we have 50 times d phi dx plus 5 d phi dy is equal to 2 times d squared phi dx squared plus d squared phi dy squared plus 3xy. Okay. So first thing we're going to do, or our first thing that we notice is we have a two-dimensional equation because we have derivatives in both x and y. So let's write out what our parameter values are. Okay. So first, let's pull out the value for u. So first, we can see that we have a coefficient of 50 in front of d phi dx. So that tells us that u is equal to 50. Okay. Next, let's take the coefficient in front of d phi dy, and that's going to be our v term. Okay. Okay, so our v is going to be 5 because that's the number that's in front of d phi dy. Okay. So then now let's write out our diffusion coefficient. So our diffusion coefficient is going to be the term that's in front of the double derivatives. So in this case, that is 2. Okay. Okay. And then finally, we have our source term, or our source term here is going to be 3xy. Okay. And so we're going to solve it on the following domain. So we have a 4x4 grid. So we have 4 cells in each of the X and the Y direction. So they're given by those, okay? And our boundary conditions are the following. Okay, so on the bottom, we have a flux boundary condition of 0. On the left side, we have a Dirichlet condition of phi is equal to 50. On the top, we have a Dirichlet condition of phi is equal to 50. And on the right, we have a Dirichlet condition of phi is equal to 25. Okay. And so what we want is for this first part of the problem at least, is that we're going to derive the finite volume equations for each of the cells. Okay. All right. Any questions on the setup of the problem? Okay. So the first place, let's start with the interior cells, because we have an equation that we can just directly apply with it. Okay. So in this case, we only have 4 interior cells, so that's going to be 6, 7, 10, and 11. So it's going to be all of these guys. Okay. Because for those cells, we have the equation that we looked at earlier. Okay. So we have U delta divided by 2 minus K phi sub E plus minus delta or minus V delta divided by 2 minus K times phi sub S plus minus U delta divided by 2 minus K phi sub W for the west, okay, plus V delta divided by 2 minus K phi on the north plus 4K phi sub C is equal to Q of XC comma YC delta squared. Okay. So if we plug in all of our parameter values from the problem, we get the following numbers. So we get 4.25 phi on the east minus 2.25 phi on the south minus 4.5 phi on the west minus 1.75 phi on the north plus 8 phi C is equal to 3 over 16 times XC YC. Okay. Okay, so then from here we can basically just apply this to all the central cells. So I'll do one of them just so you can see. Okay, so let's do this for cell 6 first. Okay. So then we're going to input basically the east, the south, the west, and the north neighbors for 6, and then just plug those in. Okay. All right, so first we have 4.25 times phi east. So the east neighbor for 6 is going to be phi 7. Okay, that's going to be minus 2.25, the south neighbor for 6, so that's going to be phi 2. Okay. Okay. Now it's going to be minus 4.5 times the west neighbor for 6, so that's going to be 4.5 times phi 5. Okay. So that's going to be minus 1.75 times the north neighbor. So the north neighbor is going to be phi 10. Okay. Times 8 times, plus 8 times phi 6, where phi 6 is phi sub c. Okay. Okay. So that's the equation for the interior cell 6. And then we can apply the same kind of methodology for phi 7, for cell 7, cell 10, and cell 11. Okay. All right, any questions on this? Okay. Okay, so then now we need to start doing some of the boundary cells, okay? So we're gonna follow the same kind of methodology that we talked about before, where we're only gonna modify one of the integrals if it's on the boundary, okay? So let's first take a look at cell number 2 and cell number 3. Okay? And these guys are on the bottom side of the domain, so they both have a flux condition on its south face. Okay. And so just like we talked about before, so since the flux condition is only on its south side, the only integral that we're going to modify is the south one. Okay. So the south integral is given by this. So it's integral of phi v dot n minus k d phi dy, since we're on the south face, okay, times ds, okay. Where this guy is, remember this is our flux. And luckily for us, the flux condition on this case is 0, so we're just going to set this equal to 0. Okay? So this is going to be 0 times dx, which is just going to be 0. Okay? And so let's plug this in while keeping all the integrals the same. Okay? Okay. Okay. So then this is the equation that results. So we have u delta divided by 2. So first we have the east integral. So the east integral, we have u delta divided by 2 times phi sub c plus phi sub e, okay, minus. And this is, we've already assumed that delta x is equal to delta y. Okay. So it's going to be minus k phi sub e minus phi sub c. Okay. So all this right here, this is the east integral, which we've kept exactly the same. Okay. Okay. And so the next one that we put in is the south integral, which in this case we say is just going to be equal to 0. Okay. Okay. And then we need to input now the west integral and the north integral. Okay. All right. So before we do that, are there any questions on this page? I don't know if you guys can hear it, but we trapped our cat inside my bedroom just because she's been really aggressive in trying to beg for food. So I've been listening to her yowl kind of this entire lecture, but I don't know if you guys can hear it. Okay. So then now let's do the west and the north integrals. Okay. So on the west, we have the following expressions. We have minus u delta divided by 2 times phi sub w plus phi sub c, okay, plus k phi sub c minus phi sub w. Okay. So this is the west integral, which we've kept exactly the same. Okay. And then finally, we have the north integral. So that's plus v delta divided by 2 times phi sub n plus phi sub c minus k phi sub n minus phi sub c. Okay. Okay. And all this is equal to our source term. So it's going to be 3 over 16 xc yc. So then let's, we can, now that we've, added all our integrals together, we can plug in for all of our parameter values and we can simplify it. Okay. Okay. So then if we do that, we end up with the following coefficients. Okay. So we get 4.25 phi east. Okay. Minus 4.5 phi, I think that's west. Minus 1.75 phi north. Okay. So notice we don't have a phi south because that was taken out by the south integral. Okay. Plus 6 phi sub c, okay, is equal to 3 over 16 x c y c. So that's the finite volume equation that we get from cells 2 and 3. Okay. So you can just plug in the neighboring values for 2 and 3, and then that'll give you 2 more equations. Okay. All right. Any final questions on this? Okay. So we're out of time for today. So on Wednesday we'll pick this up and we'll do the Dirichlet boundary conditions, and then we'll also do the corner ones, and then we'll go through the MATLAB code just to see how you guys can implement it in MATLAB. Okay. So then after that we're going to start going over higher order schemes, which is what you're going to need for the project. Okay. All right. So I'll see everyone on Wednesday. Please get some rest, everyone. Last week was pretty tough, and hopefully you guys can rest easy this week a little bit. Okay? So stay safe, stay healthy, and I'll see you guys on Wednesday. All right, thanks for tuning in, everybody.
Professor, I got one question.
Sure. What's up?
Every time we do this on the homework, do you want us to work it out from the integral standpoint?
For the boundary conditions, that's usually the safest way that you can work it out. I'm not going to be checking that explicitly, but it usually helps me the most to work it out from the integral. But if you see a pattern that you can exploit and you can plug it in, then you can use that as well. But usually working out from the integral is the safest way that I found. But
okay.
But yeah, just use what works best for you.
Okay then. Thank you.
Yep. All right, so if there's no more questions, I'm going to sign off. So I'll see you guys on Wednesday.